In this class, we are starting unit 4, and in this unit 4 actually you have two parts. One is boiling and the other one is condensation. Okay, to briefly introduce to you what is boiling. In boiling, what happens? Liquid will convert to vapor, and in condensation what happens? The reverse will happen, that is vapor will convert to liquid. So that is the basic difference between your boiling heat transfer and condensation heat transfer. But so far in till unit 3, what we have seen is we have seen heat transfer without phase change. Okay, so till unit 3, whatever the heat transfer we have seen, that is the heat transfer without phase change. When it comes to this case, no, in unit 4, what we do is we actually have heat transfer of two phases. It is a two-phase heat transfer, that is from liquid to vapor or vapor to liquid. If it is going from liquid to vapor, we call it boiling. Okay. So in the first part of this unit 4, we'll be seeing this boiling section. So in boiling, we'll be seeing so many cases now. Okay. See here, you can see there is a water in this vessel here. This is a vessel here. In this vessel, there is water, and this water is being heated as the vessel is getting heated. Okay. Over a period of time, what happens? This liquid will convert into the vapor. As the liquid converts into the vapor, what you're going to have there? You have boiling happening. Okay, the same can also happening when you have a tube and water is flowing in the tube, and when this tube is maintained at very high temperature, something like 200 degrees centigrade, then water will get boiled. Okay, because the boiling point of water is 100 degrees centigrade at the atmospheric conditions. Okay, so when I say that boiling point of the water is 100 degrees centigrade, what is the pressure at which that is valid? Somebody respond. Whenever I say that boiling point of water is 100 degrees centigrade, then this statement will be valid at what pressure?
Atmospheric pressure.
Atmospheric pressure.
At atmospheric pressure only this is valid. Okay, this is also called as a Tsat, that is the saturation temperature. The saturation temperature for water is 100 degrees centigrade when you have the pressure in the atmosphere as 1 bar. Okay, if the atmospheric pressure is going to vary, that is, if it is going to fall below this 1 bar, this temperature also will fall down. If it is going above this 1 bar, this temperature also will go above that, because P is proportional to T. So P sat also will be proportional to T sat. All right. All right. So what is the meaning of the saturation? We have to understand here. Saturation means if I have a bottle here, let me take a bottle here, something like this. Okay. In this bottle, I have filled the water till its brim. Okay, it is full of water. Okay. Can I fill the water anything here? Okay, till the brim I have filled. So there will not be any chance for filling further. There is no chance for filling further. This state is called as saturation state. Okay. Same way, in case of water also, it can it can take heat in the liquid form only till 100 degrees centigrade at the atmospheric pressure. If you go beyond this 100 degrees centigrade, it will start evaporating. That is, it doesn't have the ability to take anything more. So here, in this case, 100 degrees centigrade will be the boiling point temperature of the water. Anyways, if you are boiling it in a vessel like this, it is called as a pool boiling. It is called as a pool boiling. In the pool boiling, what happens? You will have a vessel, and in the vessel, you will be heating it up. When you are heating it up, the bubbles will form, the water will convert into the vapor. All these things will happen any kind of boiling. But if you do that kind of boiling in a vessel, it is called as a pool boiling. Okay. Essentially, in pool boiling, mm, uh, bulk fluid motion. Yeah, here it is written. The bulk fluid motion is not essentially present, okay, in pool boiling, whereas in flow boiling, bulk fluid motion is present. That is the essential difference between your pool boiling and flow boiling. Okay, whatever boiling you do on stove and on stove with the vessel is the case for pool boiling. Whatever the boiling you do in the tubes of heat exchanger or an evaporator is called as a flow boiling. That's the difference between your pool boiling and flow boiling. You should understand what is a pool boiling and flow boiling. Right. What is the next kind of a classification? Next kind of classification is a subcooled boiling one. The other one is a saturated boiling. See, if the water is at 100 degrees centigrade, that is a saturated temperature. But here in this first case, it is only at 80 degrees centigrade. Since it is at 80 degrees centigrade, it is less than 100 degrees centigrade. Okay, that is, it has not reached its saturation. So whatever the region that is below the saturation is called as a subcooled region. That's why if you are boiling it less than the uh, T sat, less than T saturation, then it is called as a subcooled boiling. If it is almost equal to Tsat, then it is called as a saturated boiling. Okay, this can happen both in the uh, bubble itself, sorry, both in the vessel itself. We call it as a pool boiling. All right, let's move on. And not only that, not only in pool, you can also have this in flow case also. Okay, it is not restricted to pool. Right, moving on, you have one more thing called as a natural convection boiling. Okay, natural convection boiling means what? Here, whatever the fluid that is there, this fluid will go from a lower temperature to higher temperature. But the rate of increase of this lower temperature to higher temperature makes the difference here. Okay. So based on the increase of temperature, we actually classify this way. Okay. In the first classification, the increase in the temperature is very small for longer duration. Okay. But as you go further in the nucleate and transition boiling, for small duration also, you will have huge temperature differences. Okay. This is very, very important kind of classification that you should know. The first thing is natural convection boiling. In natural convection boiling, what happens? You will have the less temperature increase for long duration. Okay, this is called as a natural convection thing. When it comes to nucleate thing, what happens is high temperature increase. for small duration. Within the small duration itself, it will increase the temperature like anything. Okay, why is this difference coming? It is depending on the temperature that you are maintaining here. Here in this case, you are maintaining only 103 degrees centigrade, whereas here you are maintaining 110 degrees centigrade. Because of this difference, what happens? The rate at which the water is getting heated will get influenced. So that rate, that rate is actually influenced by the temperature that is maintained on the surface of the heater here. Okay, so if the increase in the temperature of the water is less for longer duration, then you call it as natural convection boiling. If the increase in the temperature is high for the small duration, then we call it as a nucleate boiling. Why you are calling it as a natural convection and why you are calling it as a nucleate boiling, that we should understand. When I say nucleate, nucleus means here we mean to say bubble here. Okay, you will have bubble formation. See in this right side case, nucleate boiling case, you have bubbles formation shown here. Whereas here, no bubbles. In case of natural convection, no bubbles are formed. But there is boiling happening, but that is happening below the saturation temperature kind of. So this is called as a natural convection boiling, where you don't have the bubble formation. When it comes to nucleate, there will be a bubble formation. And if you keep on heating further, okay, if you keep on heating further, there will be something called as a film formation here. When you see this film formation, so as you keep on heating it, what happens is when the temperature is very much high, right at the moment when the water touches that particular surface, it will get vaporized. Okay, immediately it will get vaporized. So that particular high temperature will be maintained here, and immediate film is formed here. Okay, this we call it as a film boiling case. Okay, this is a nucleate boiling case where you have nucleus coming. Where when the film is formed here, a film of vapor. This is actually film of vapor that we call it as a film boiling case. In between the nucleate boiling and transition boiling case, you will get something called as transition boiling. Okay, in between nucleate and film, you will get transition. Okay, here the film is not completely formed. The pockets of film is formed here. As you can see, the pockets of film is formed here in this case. So this is the thing regarding this is very important explanation I tell you, and this we will get in the examination also. This curve is actually full boiling regimes curve. Okay, very important for exam. Again, this curve is entirely based on the explanation that I told you just now. Most of the times from boiling, this question is asked. Okay, so listen to it carefully. So the same kind of phenomenon is now explained differently for understanding pool boiling regimes. So for that, you will have a vessel. In this vessel, you will keep a heating element and you will maintain a temperature of 110 degrees centigrade, and you keep heating the water using this heating element. And when you keep heating it at 1 atmospheric pressure, what happens? That thing we have drawn here. Okay, you have shown temperature on x-axis. On y-axis, you have shown the heat transfer, Q. Okay, so here, as the temperature is increasing on x-axis, you can see the heat transfer is also varying here. See, here you basically have three stages. First one is free convection case. Second one is nucleus boiling case. Third one is film thing. Okay, the same thing that I have told you here. Natural convection. That is a free convection. First one. The second one is nucleate boiling. Third one is film. Natural nucleate, and film. These three things. Natural nucleate film, natural nucleate film. These are the three cases that you are going to get in this pool boiling regimes. So free convection, nucleate boiling convection, and film boiling convection. So in these three, what happens is, in the first case, let us see. In the first case, what happens? Free convection case. So during the free convection case, I told you already that for long duration, you are going to have small temperature rise. So in this process, what happens? As the temperature increases, the heat rise, the increase in heat transfer or increase in H. Okay, Q is equal to H delta T, we know it. So in case of convection, heat transfer is majorly influenced by H. Q is directly proportional to H. So if H is increasing, Q is also increasing. So as the temperature increases, the increase in heat transfer is not so rapid. It is gradual increase. So that's why you call it as a free convection case. Okay? This is the first stage of the pool boiling regime. Next case is your nucleate boiling case. But this nucleate boiling is further divided into two, actually. This is the second and the third are actually nucleate pool boiling case only. But in the first case, what happens is here bubbles will condense. Okay, whereas in the second case, bubbles rise to the interface. That is, here bubble collapses. Here bubble rises. In the first case, whatever the bubble that has formed from the surface, it won't reach till the surface. Okay. But whereas in the second case, it will reach the surface. Why is it happening? See, in the first case, what happens is the temperature is not high enough for the bubble to sustain it. Okay. So since the temperature is less, the temperature that is surrounding the liquid. Okay, let me show it here. Here, if you have a bubble here, okay, in the first case, the temperature that is there for the water surrounding this bubble is less. That's why this bubble will not try to increase. Okay, the temperature is actually preventing this bubble to raise. Okay, so the bubble will collapse. But if the temperature is more for this bubble, then this bubble will rise till the top. Okay, so that's how nucleate boiling case is divided into two stages. So first, bubbles will form, the nucleus will form, but they collapse. But in the second case, bubbles will rise. When you reach this stage, the third stage, the increase is so huge. In very short duration, you will have so much of increase. This is called as a nucleate boiling case. Okay, the increase in the second stage is also high compared to your free convection, but that is less compared to that you have in the third stage of your nucleate boiling case. So that is the thing regarding the nucleus boiling. And moving on, what happens is there is a formation of film. Okay, so you will have something called as a spheroidal state beginning. As the spheroidal state begins, what happens is film formation will start. See, film formation, what it has done, it has reduced the temperature. Isn't it interesting? It is interesting. Okay, why the temperature has reduced here? See, the temperature will reduce here because here there is a formation of film here. When you have this film, what it does, it has a vapor in it. Okay, when vapor is there, what happens? Heat transfer will not happen at a higher rate because the Cp of vapor is something around 1 kilojoule per kg Kelvin. Previously, you used to have water here whose CP is around 4 kilojoule per kg Kelvin. Now, what happened? The CP value has reduced hugely, and even the K value also you can compare. Even the alpha value also you can compare. So when you compare these values, they will hugely decrease. When they decrease, what happens? The H value will decrease. When the H value decreases, there is a reduction in temperature. That's why you can see there is a drop here. This is the drop that is happening. Okay, so this is a kind of partial nucleate boiling, and it is also called as a unstable nucleate boiling. Okay, so for some time that will happen, and then you will have stable film boiling. In partial film boiling, what happens is you will have formation of pockets of film. Here, pockets of film are formed, and as you move ahead, complete film is formed. Complete film is formed, and if you move further, the radiation will come into the play. The temperature will increase very hugely. That's why very high temperature is obtained here. You have to take the radiation into consideration. See, radiation will be significant only at the higher temperature. If the temperature is taken here, the temperature to the power 4 is taken. Temperature to the power 4 will be very significant as the number increases. Okay, so maybe around 400 degrees centigrade. If you come here, plus 273, power 4, if you do, the value is very huge. Okay, you cannot neglect that value. So along with the convection, you have to consider the radiation also here. Even sometimes the radiation will cross the convection heat transfer here. So majorly in the case of this one, the radiation case, the heat transfer by radiation will be more compared to the heat transfer by convection. So this is how your full boiling regime looks like. Okay, this is the very important for exam. Very important for exam, even for your mid exam and the end exam. This is very important. Draw this figure neatly. Again, not like what I have written everything here. You need not write what I have written with my red color, whatever that is there in the black there. If you can show it, the numbers are not very important. Okay, forget about the numbers. Here also you have numbers. Numbers are not very important. We need not by heart these numbers. We need only show temperature on the x-axis. Even also you can show delta T. Both mean the same. On the y-axis you can show Q or H. Okay. Then draw it. This curve should be clearly shown, and then these three things. Let me remove all this. Oh, it's there. Uh-huh. Yeah, here it is. So this way you have to draw it. So if you have any questions, you can ask, or I will proceed to the next thing. Yeah. So if you have to see the real time thing here, this is how nucleate boiling case will look like. You can see the formation of the bubbles here. Here you can see the bubbles are formed and they're trying to reach the top. Some are reaching top, some are not reaching the top. During the transition boiling, you can see there is a formation of film here. As you move further, this is actually film. This is surface. This is surface. These are pockets of film. Pockets of film means vapor here. Then this is film formed here. Purely throughout there is a film formed. This is called as a stable film boiling case. Okay, out of this we will have radiation boiling also. I hope it is clear. If you have any questions, you can ask, or I will stop the share and move to the problems. See, coming to the boiling problems, the most important thing is using the data book itself. Okay, nothing great here. You have to use your data book appropriately here. If you are in position to use your data book appropriately, you're done. That's it. So have it in mind clearly. Using the data book is the key here. Okay. So let me open my data book also. So where is it? Oh, yeah. Here we go. Go to the page number 151 in your data book. In your data book, go to page number 151. 150. Here you have the formulas for boiling. Again, in boiling, you have two cases. The first one is nucleate pool boiling. The second one is film boiling. The two stable film boiling when the horizontal tube is taken and radiation prevails. Only based on this, you will get questions. So now using these formulas, you have to solve. Till here, these are the formulas of pool boiling. So today we will complete this pool boiling, and tomorrow, maybe in the next class, we will see the film boiling. Okay. So with that, we will complete the boiling. It's quite simple, nothing great. So that's why I'm telling it right in advance. So here you have a question. In this question, what he has given? He has given water. So water is given, and then it is at 100 degrees centigrade. So you write the Tsat here. The Tsat is 100 degrees centigrade, and the boiling area is equal to 0.05 meter square. The copper boiler is there here, and it is heating it. Okay. So what you take it as temperature of the wall. It is 110 degrees centigrade. In your data book, this temperature is called as a TW, that is a surface temperature. Okay, TW. I'm showing it as TW, and nothing else he has given. He's asking you to find the surface heat flux. Heat flux means what? Q by A. What is the value? He's asking. Also, he's asking what is the rate of evaporation, means it's kg per second. You can say mass flow rate. This is the question he has given. Okay. So what he's asking? He's asking you to find QA. Go to your data book. Where is the formula for QA? Okay, the formula for QA is right at the top. This is the formula. This formula, you take it and put there. Here, let me write that Q by A is equal to mu L. That is actually mu L. It seems as 1 to you, but it is L. If you confuse, correct it as L, because you can see here on the right side of your data book is written what he mean by mu L. It is a dynamic viscosity of the liquid. So it is mu L actually into HFZ into the Z into rho L minus rho V. That is V actually. L means liquid, V means vapor by sigma whole to the power of 0.5 into the C of liquid again. CL. Where has given that C? He has given it here. CL means specific heat of the liquid. We can observe in the data book. Okay, the CL is given, then delta T, and then CSF HFZ into Prandtl whole to the power of Prandtl power n whole to the power of 3 whole to the power of 3.0. I'll put 3 here. Okay. So you have taken simply this is taking the formula from there. After that, you have to get each term in it. Okay. If you term each term, if you get each term from the data book and substitute, you are done with Q by A. That's it. Okay. Q by A, he's asking you to find. You will find that Q by A. Okay. So, how to get mu L here? Tell me. What is a mu L? Speak out somebody. మాట్లాడమ్మా వింటున్నారా మీరు అసలు?
Dynamic viscosity of liquid.
Yes, it is the dynamic viscosity of what? Of water you have to take. If you have to take it for water, what you have to do? Go to the data book. Which page will you go?
What?
Page number 42 is for air. Will you go for air? Air is given in question. చెప్పండి
30.
ఏమి ఇచ్చాడు?
Water.
It is water given in question. So you will go to page number 30. Here it is. You will go to page number 30 కదా ఇది 30 గలండి వాటర్ తీసుకోండి వాటర్ తీసుకున్న తర్వాత యూ కెన్ టేక్ ద మ్యూ హియర్ ఫర్ డూ యూ హ్యావ్ మ్యూ హియర్ ఉందా డైనమిక్ విస్కాసిటీ ఇక్కడ యూ డోంట్ హ్యావ్ డైనమిక్ విస్కాసిటీ హియర్ సో మ్యూ is actually product of rho into mu. Okay, that is a dynamic viscosity, right? So where will you take these properties? That is the point. Here you have so many temperatures. You have so many. Among this, which temperature will you take in this question? Chapman?
Delta T.
You will take it at delta T na.
100.
TW plus Tsat V2.
Mm-hmm.
100.
TW plus 100. Inka? Any more answers?
110.
110. Inka? Say all the properties to take it at 100 degrees centigrade. Okay, because at Tsat this particular process is happening. Okay, for example, in this question only he would have asked you Q by A critical. This he must have asked you. If he has asked this, then he has given a special case. Okay, the properties at TW plus Tsat by 2 he has given. So then you will take that average value and then take it. But here in this question he has not given. So he is only asking you the Q by A. He is not asking you Q by A critical or the maximum heat flux. So what you will do, you will solve it using the first one at 100 degrees centigrade itself. So if you have to solve it at 100 degrees centigrade itself, at 100 degrees centigrade, mu L. How to get this mu L here? How to get from the page number 30? Let me write this page number 30. The side of page 30. Mu L is equal to rho into nu. This is equal to the rho value at 100 is 961. Nu value is 0.293 into 10 to the power of minus 6. So we are done with mu L. We move to the next thing. What is the next thing? HFG. Here in this expression, HFG is required. So where do you get this HFG? Somebody tell me. చెప్తారా హెచ్ఎఫ్జి ఎక్కడ దొరుకుతుందో? So you move to page number 153. Move to page number 153. Here you can see latent heat of vaporization of water means what? HFG only. Okay, HFG means what? It is a latent heat of vaporization. Okay, that will be given even in your this thing. in this one, HLG. You have to get from page number 153 and 156. He has mentioned very clearly here. So move to that 153 page. At 100 degrees centigrade, you take the value. What it is? 2256.9 kilojoule per kg here. Very important thing is kilojoule per kg. That should be 10 cube into joule per kg. Okay. And this you have got it from page number 153. So we're done with HFG. What is the next thing here? G you have. So G means what? Acceleration due to gravity. Okay, you can read that G in the data book also. Okay, where is this? Where it is? In data book, if you go, the G will be written somewhere. You can see for yourself. Yes. G is acceleration due to gravity. 9.81 meter per second square is clearly given in the data book. 9.81 meter per second square. Okay, you know it. No page number is required for this. Then moving to rho L. Rho of liquid. What is the rho of liquid? Somebody tell me. Just now we've seen it.
961.
91.
61. 61 kg per meter cube. So again, you got it from page number 30. Yeah? 30. So royal is over. Then what you have is rho nu. Rho V actually. Rho of vapor unit. Density of vapor. How to get this? Tell me. Density of vapor ఎలా తీసుకోవాలో చెప్పండి.
Air.
of steam.
Yes, the density of steam. Correct. Where do you have that value? చెప్పండి అది ఎక్కడ ఉంది డేటా బుక్ లో స్టీమ్ ఎక్కడ ఉంది
7.
నెంబర్ నెంబర్
47.
47. Here it is. Page number 47. We have the steam properties. Okay. So for steam, the value of density at 100 degrees centigrade, what it is 0.598. You can see it here. Density measured in kg per meter cube. So substitute that 0.598 here. From page number 47, you got it. So you're done with rho V. Then you have to get the sigma. What is the sigma? Tell me. You look at your data book.
Surface tension.
It is surface tension. Surface tension. Sigma is surface tension of the liquid and vapor interface. Okay. So where do you get this? ఇది ఎక్కడ దొరుకుతుంది మనకి ఇక్కడ రాసేటువంటి
153.
155 లో దొరుకుతుందని అక్కడే రాశారు. సో యూ గో టు పేజ్ నెంబర్ 153 and 155. Here it is. Surface tension is here. Surface tension of water against air, you can take it. So at what value you have to take? You take it at 100 degrees. 0.0588 is the value. What is the unit of surface tension?
Newton per meter.
Force per length. Newton per meter. So it is from page number 153 again. So you're done with sigma. Then you need Cl. Cl means Cp of liquid. Okay, so for that, what is the page number? Water page number you have to go. So, water page number is in page number 30. Cp of water at 100 you need, it is 4216 joule per kg. So write that value here, 4216. This is from page number 30. What is the next thing you need here? Delta T unit. What is the delta T? చూసి చెప్పండి మీ డేటా బుక్స్ నుంచి. It is T
W.
W minus T sat. That is equal to 110 minus 100 in our case. Okay. This is again like page number 151 only. Delta T అయిపోయింది. Next, what is that thing? CSF. CSF. CSF means what? CSF అంటే ఏంటో చెప్పండి డేటా బుక్ చూసి. It is skin friction coefficient అంటారు. CSF అంటే it is in page number 152 అని ఇచ్చారు ఇక్కడ. Go to page number 152. CSF. అదేలే స్కిన్ ఫ్రిక్షన్ కోఎఫిషియంట్ అమ్మా. SF అంటే స్కిన్ ఫ్రిక్షన్ అని. ఓకే, ఇట్ విల్ బి బిట్వీన్ టూ materials, water and copper, water and platinum, water and brass, like that. Okay, so here in the given question, which combination will you choose? చెప్పండి, మనం ఏ కాంబినేషన్ చూస్ చేసుకోవాలి ఇక్కడ? వాటర్
Water.
ఉంది మనకి,
Water and copper.
కాపర్ ఉంది మనకి. సో వాట్ ఈస్ ద CSF వాల్యూ దట్ యూ షుడ్ టేక్? 0.013 అనేది తీసుకోవాలి మనం. 0.013 for water copper combination in page number what? 152. CSF అయిపోయింది. నెక్స్ట్ ఏముంది? HFG. ఆల్రెడీ మనం తీసుకున్నాం HFGని. నెక్స్ట్ ప్రాండల్ మిగిలింది. సో ప్రాండల్ దేనికి తీసుకోవాలి చెప్పండి?
Water.
ఫర్ వాటర్ యూ హ్యావ్ టు టేక్. ఎక్కడ ఉంది వాటర్? వాటర్ కదా. ఫర్ వాటర్ ద వాల్యూ ఇస్ 1.740. 1.740 ఫ్రమ్ పేజ్ నంబర్ 30. ప్రాండల్ అయిపోయింది. నెక్స్ట్ ఇంకేముందేమో? ఎన్ ఉంది, ప్రాండల్ పవర్ ఎన్ ఉంది. ఎన్ ఎంతో చెప్పండి?
1.
పేజ్ నెంబర్ 151లోనే మీరు చూస్తే డేటా బుక్లో ఎన్ ఈజ్ ఈక్వల్ టు 1 ఫర్ లిక్విడ్స్ అని ఇస్తాడు, ఎన్ ఈజ్ ఈక్వల్ టు 1 ఫర్ వాటర్ అని ఇస్తాడు. చూడండి ఇక్కడ ఎన్ ఈజ్ ఈక్వల్ టు 1 ఫర్ వాటర్ అనేది మనకి డేటా బుక్లోనే ఉంది. సో ఎన్ ఈజ్ ఈక్వల్ టు 1 ఫర్ వాటర్. సో యూ టేక్ ఎన్ యాజ్ 1 హియర్. So that's it. You have to simply substitute and get the value of Q by A. Substitute చేసేసి నాకు చెప్పానమ్మా వాల్యూస్. ఫస్ట్ మ్యూఎల్ ఉంది. మ్యూఎల్ ఏమో 961 ఇంటూ 0.293 ఇంటూ 10⁻⁻6. తర్వాత హెచ్ఎఫ్జి ఉంది. HFG value is 2256.9 into 10 cube. 10 cube is very important number. Many times you will miss this 10 cube here. So we miss it. All the possible answer. It is, see, boiling questions are simple substitution. Proper substitution if you do, you can solve it. Okay, many times students will miss the substitution only. 9.81 is G and the rho L. liquid యొక్క density 961 minus fluid density 0.598 by sigma. The sigma value is 0.0588 whole to the power of 0.5 into the Cp of liquid. I have to substitute 4216 into the delta T. It is 110 minus 100. Simply 10 you can put by the CSF value is 0.013 into the HFG 4216 into the Prandtl is 1.74 whole to the power of 1 and to the power of 3 is cube. Substitute this into your calci properly. నా సజెషన్ ఏంటంటే అమ్మ క్యాల్సీలో సబ్స్టిట్యూట్ చేసేటప్పుడు అంతా ఒకేసారి సబ్స్టిట్యూట్ చేశారంటే పోతుంది. సో 3 డిఫరెంట్ టర్మ్స్గా మీరు సబ్స్టిట్యూట్ చేసుకుని ఆ 3కి మీరు మల్టిప్లై చేసుకోవడం బెస్ట్ థింగ్. కొంతమందికి మంచి క్యాలిక్యులేటర్లు ఉండి మొత్తం సబ్స్టిట్యూట్ చేస్తున్నారు, వాళ్ళు ఖచ్చితంగా మిస్టేక్ చేస్తున్నారు. సో నా రిక్వెస్ట్ ఏంటంటే యూ హ్యావ్ 3 different terms 1, 2, 3. Then you calculate those 3 things separately in the calculator and then substitute values here. ఇంత అని ఆ తర్వాత మూడింటికి మల్టిప్లికేషన్ చేసుకోండి. అది బెస్ట్ థింగ్. మోస్ట్ ఆఫ్ ద టైమ్స్ పాయింట్స్ పవర్ 5ను క్యూబ్ని పోగొడుతుంటారు, అవి చూసుకోవాలి. ఓకేనా?
143.2.
క్యూబ్ అయ్యే యువర్ టెలింగ్ డైరెక్ట్లీ.
Yes, sir.
కరెక్టేనా? So whatever, you will get some Q by A value. Fine, you got Q by A value, some value you got. You will get it in watt per meter square. This is fine. But point is here, he is also asking you to find the rate of evaporation. So how will you find the rate of evaporation here? This is again by simple thing. See, Q by A you have with you. Area value he has given to you. So you can substitute area. So that will give you Q value. Q ento meeku telusu. When you know Q, this Q is actually equal to m dot into HFC. So m dot is required here. M dot is equal to Q by HFC. You have Q with you, HFG with you. Substitute the values. You will get the rate of evaporation in kg per second. Is that clear? Q is in watt and HFG is in joule per kg Kelvin. This is equal to watt means what? Joule per second. Sorry, Kelvin will not be there here. It is kilojoule per kg. That's it. That's the HFG unit. Joule per kg. And the joule get cancelled. So unit of this m dot will be kg per second. So what you're getting here is m dot, that is the rate of evaporation in kg per second. So solve it for yourself. These two things are required in the question.